All right, so we'll continue our discussion on boosting. We went through very quickly an adder boost algorithm last time. So we'll see the algorithm again, and we're going to the details of how to select the parameters in the algorithm. Sorry about the noise. So just to review again, so add boost is specifically you have like hypothesis concept class capital C, which is mapping from the input space to the label space, and you have a binary label -1 + 1, and your hypothesis class also, is being able to assign either -1 or +1 to your examples, and your sample. It has M examples, just as we usually assume. So your base classifiers could be drawn from these hypothesis class. And specifically, I want everyone to pay attention to this epsilon t, which is the weighted empirical loss on my sample for the specific HT in this hypothesis class, okay? So it is specific to the HT, and it's also specific to the sample, S. It's also, very importantly, is a weighted empirical error because the DT is a probability vector. So essentially, you can think about DT as how importantly you value each of the example when you're calculating the loss. Okay. All right. So that's a recap. And as we said last time, boosting works in a way that is trying to ensemble in a smart way the weak classifiers, right? So, in this case, we have 3 weak classifiers, but the weak classifiers are not, arbitrarily selected. It is selected in a way that the first weak classifier could just do classification on the examples that are just, with uniform distribution. So by uniform distribution, I don't really mean the underlying distribution of data is uniform. Maybe I should say uniform empirical distribution. I just mean that when I calculate my empirical error, I just use 1/m for each of the example, for each of the losses induced from these examples. Okay, so
question on that.
Right.
So should that equations be h of t equals arg min over h?
Oh, yes, that is a good point.
Okay, great.
Yes,
yeah.
Sorry, that's a very obvious typo. Okay, yeah, exactly. HT is not a empirical loss, right? So it is essentially the arg min of this quantity here. So essentially, I haven't talked about this yet in my last lecture, and I don't know how to motivate it right now, but I will tell you later when, we think about the algorithm. After we read the pseudocode, we'll see why we have this kind of loss rather than a 0-1 loss, okay? Also, I guess the motivation of the DT here is just, the empirical distribution vector, probability vector. Okay, that's a very good point. Okay, so you get a classifier 1, and then you put more weights onto these classifiers. So you can see here, these are wrongly classified. So you kind of amplify them because, see, so, if minus y1 htx1, sorry, minus yi htxi, if this term is negative, right? Then that means the the hypothesis has been mapping your data to a label that is different from your true ground truth, yi. Therefore, when it's negative, then this thing will be positive, then it's gonna be an exponential to the power, exponential of a positive thing. So it's gonna be large, right? So you are amplifying the distribution on this ith data point, okay? And this ZT here is just to make sure that this is a distribution vector, okay? All right. Well, so then, you do that again, and essentially, you will get these also amplified points, and then the weak classifier 3 is going to learn that again based on the modified probability vector dt. Okay, so you get somehow a weighted voter to do a combination. It's actually linear combination here, a linear combination of the weak classifiers, but the alpha t is not given yet. Okay, so now we've seen this through a picture to get a very intuitive understanding of how adder boost work. But now let's look into the details as we promised. So the add boost algorithm here, I kind of put the pseudocode here, right? So what happens is at the initial stage, which is basically weak classifier 1, you have this so-called uniform empirical distribution, 1 over m for each of the data points, right? So now as training goes, right, so t means you're now at the t's weak classifier. What do? You would select ht such that the epsilon is smaller than 1 over 2. Again, I didn't talk about the training algorithm here, right? I'm just saying you select ht. I don't know how you do that, but somehow you select this weak classifier as long as the empirical, the weighted empirical error evaluated on this ht, it's smaller than 1 over 2. So it's slightly better than random guess. Okay, so again, I didn't tell you how I select HT, but I just wanted to make sure that HT satisfies this property here. Okay, also now what happened is, once you get HT, you can of course evaluate this epsilon t here. Once you get evaluated that, so this is very important, you will get this alpha t. Okay. So this alpha t turns out to be half logarithm 1 minus epsilon t divided by epsilon t. This is very important. And, I don't know how to motivate it right now, but after we see the proof, I will get an understanding of why we select alpha t to be that way. Okay. So this essentially is I would say reverse engineering. You wanted to get some good property, and you can somehow reverse engineer it to, figure out what's the optimal value of alpha t. Okay, so you somehow get that. Now what happens is essentially you will get a normalization term CT, which is also, it's quite difficult to see why, we do it this way. Sorry, this is blocking your view. I'm going to erase these. Okay, so what happens is, again, just like what we said before, we're going to update the weights. So let's see. So the weights is going to be updated this way. So you have the alpha t here, exponential minus alpha t YIHTXI. So YIHTXI can only take 2 values, -1 or +1. Okay, if it is -1, then it's wrongly classified. Then this exponential is going to be exponential of a positive number. When it's correctly classified, it's going to be an exponential of a negative number. So, overall, if it is, if you wrongly classify it, the empirical distribution will be larger. You know, if you correctly classify it, empirical distribution will shrink. Okay. So in the end, you get the strong, you know, the ensemble of the weak classifiers, and essentially becomes, oh, okay, so this is a typo. I should put this outside of the for loop. So G essentially becomes a summation of alpha THT. Okay. Sorry about that. I'll fix that in the slide. Yeah, so this thing should be moved outside of the for loop because I have a capital T here. Okay. All right. So again, so right on the right-hand side here, what I'm trying to say is to understand how through this way of, you know, changing the empirical distribution, how do we do normalization to make them into, you know, how do we come up, you know, basically I wanted to say, because you wanted to make sure that dt vector and the dt plus 1 vectors are both probability vectors that they have to sum up to 1. So you want to make sure that this happens, right, through zt. So now let's see. So you wanted to make sure that the distribution dt is over S as a probability vector. So you started with uniform 1. At each round, the weights of the misclassified points will increase. So how does it increase? It will increase in this way, right? So the dt plus 1i, so the next round is gonna be the current round weight multiplied with exponential minus alpha ty ht xi. So now you can see here. So this orange term here will be expanded into this term. Okay, so this zt I should be zt minus 1i exponential of minus alpha t minus 1 yiht minus 1 xi divided by zt minus 1. Right, so this is nothing but the definition, right? So if you look at the definition here, is there a way? I don't have a laser point. I don't know. Well, so if you look at this here, right? So this is nothing but the definition. By definition, you would know this is true. Okay?
I have a question.
Yeah.
So H of T is a linear classifier.
Not necessarily.
Okay, but in our example it is.
Right.
And then this G, which is just that you said FGH, that's a summation, that's a linear combination of the H's, right? A G is a linear combination of H's. Is that right?
Right.
So this is just a linear combination of linear classifiers in our example. So the resulting end classifier must be a linear classifier.
Well, so one thing is, okay. So one thing is, although HT is a linear classifier, you're essentially dividing the, you know, how should I say? You're essentially dividing the space into two parts, right? Into two different sets. So, you know, along this set is gonna be +1, along the other set is gonna be -1. So in this scenario here, for example, let's look at this one. Let's look at this classifier. Okay. So what I really wanted to say that although it is a linear classifier, I'm not looking at the output of this linear expression. I'm looking at the threshold of this linear expression. So in that sense, that's not linear. Do you see what I mean?
You did the sign. You did the sign of the linear summation, right?
Yeah.
Okay, but if this linear summation is a hyperplane and you're looking at the sign,
So
then you
the
still
thing
get a
is,
linear boundary.
that's not true, right? So we are not doing a combination before the sine function. We're doing the combination after the sine function. Okay?
Okay. Yeah, maybe I see that.
Yeah, that is very important. And that's a very good point. So thank you very much for bringing this up. Yeah. So you can see, so yeah, you're right. If you do a linear combination of a bunch of linear linear expressions, then it's still gonna be linear. But here is, because the result of these linear classifiers is already been, thresholded, or you can think about the sine function as you just said. Now, what are you doing? You're just taking a combination of these sine functions. So that could be arbitrary. Hope that explains, right? For example, this is my H1, right? And my linear classifiers decided to probably, for example, in this region, how should I say? So in this in this H1, you probably decided that this is red and this is blue, okay? And this H2 probably decided this is red and this is blue, okay? And then this one, you've probably decided this is red and this is blue. Okay, so now let's look at this example, okay? In this example, if I look at classifier 1, it's gonna be classify me as red. If I look at classifier 2, it's gonna be classify me as red. Similarly, classifier 3 is gonna be classify me as red. So what should I do? I would just classify myself as red, right? Now let's look at this one. So this dot here, classify 1, classify me as blue. Oh, maybe I should find an example that is a little bit not easy to, because all three are going to classify me as blue here. So can someone?
Oh, classifier 1 will classify that as red.
Oh, as red. Okay, yeah, that's a good point. So yes, yeah, exactly. So classifier 1 will classify me as red, right, for this dot. But 2 and 3 classify me as blue. So by this, weighted, so-called weighted average, I still get a blue. Maybe this example, I don't know, maybe there is other examples that's more interesting, but do you see the overall message? So we're doing linear combinations of these sine functions. Okay, let me go back to this. Oh, what happened? Okay. Where was I before?
I think you just expanded the definition of dt.
Okay, thank you. Yes, right. So we were just talking about the definition of the dti. So based on the definition, it is just this dt minus 1 exponential of the thing divided by zt minus 1, right? So once I do that, a very interesting observation you will see is you can do this expansion for, recursively for t times, right? For t times. So until you get to like d1. So what is d1? d1 is essentially, d1 of I is essentially just 1 over m, right? So you get this term here after you do the recursion. So you will get this term. Now, you have to do this multiplication of these things, right? So if you see that, you're doing the multiplication of these exponentials, and essentially, because, then it becomes exponential of the summation of these terms. Okay, so this is the property of these exponential functions. And of course, don't forget about these normalization terms, zt and zt minus 1 all the way to z1. So you have to do the product of these things here. Okay, so then you will see essentially the zt plus 1 I have this expression here. So it's very interesting to see. So what is it really doing? It is doing some kind of product of the normalization terms. And then, it is weighting this 1 over m using the exponential of the weighted linear combination of the previous classifiers, okay? So you're just weighting basically you're weighting your empirical distribution 1 over m through this exponential minus y, the linear combination of these classifiers. So this is quite interesting observation, right? Any questions so far? Any thoughts? Very importantly, I wanted to mention that we selected the alpha t directly depend on the accuracy of ht on dt. So this is quite crucial here. Okay, so if no further questions, let's review the weak learning condition again. So I wanted to introduce so-called the edge of a base classifier ht for a distribution dt over s. So what is it? Essentially, it's defined as gamma t, which is just half minus epsilon t here. So if epsilon t is just as what we defined is the empirical weighted error on the sample. So like I said here, it's just the epsilon t equals to the probability of the I drawn from this dt. So what this really means is that I'm putting a weight on each of the example in my sample, and then this weight is going to be denoted by dt of I for each example I. Okay, so this, according to this weight, I'm going to evaluate whether htxy xi equals to yi. Okay, so what I do is essentially this is a trivial, like an explanation of this probability, right? So it is just summing over all the examples that this yi htxi is smaller than 0. So what that means, just means you've wrongly classified it, right? So for all the examples that you've wrongly classified it, you just multiply, you just sum up this yi htxi dt. But since this yi hi dt will anyway be just minus 1, then essentially you just have this. So this epsilon t is nothing but the summation of these empirical distribution on the wrongly classified examples. Okay, so this is one interesting observation here. The other interesting observation is, what is this 1 minus 2 epsilon t? Or what I mean is like this 2 times gamma t, right? So what is 2 times gamma t? What is the edge? The edge essentially, so the half, sorry, this is 2 times the edge. So the 2 times the edge is nothing but, by definition, is just the summation of these distribution, which is nothing but 1, right? Plus this 2 times this term. So why? Because you can just expand this epsilon t as minus of this term here. Okay, right? This is nothing but by definition. Any questions here? Right, so epsilon t is just that, right? Okay, so now what you can do is you can just expand the red term here into these two terms, right? So essentially, because you can just divide the points into two sets, the set of correct classified or the set of wrongly classified, right? So for these correctly classified, this yihtxi will be greater than 0. So you're summing over these points that satisfies that is correctly classified, and these points that are wrongly classified. For the correctly classified, because the yiht will be 1, so you can just replace the 1 here with this yiht. And for the wrongly classified, you can just do minus of this yiht. Then it's still 1. So overall, this dt summation can be divided into these two terms, okay? And once you do that, you can just, get this term because this term will cancel out. This is a minus of that, and this is a plus of that. You will cancel that out and essentially get summation of the yihtxi for both the correctly classified and the wrongly classified. Okay. Okay, wonderful. So in terms of interpretation, I just wanted to emphasize again that epsilon t is really like an empirical weighted error, whereas this edge is more like I wanted to evaluate the weighted yihtxi. So this term becomes very important. The multiplication of the classification outcome of these hypotheses with its ground truth label. Okay, so this one ground truth label and the output of become. So essentially, a lot of you might think this is very related to margin, and indeed, if we get there, we might have time to discuss margin this lecture, if not next lecture. Okay. So basically, the point is this gamma t will be just the empirical weighted average of these yihtxi here. Okay. Okay, so that's very important. But let's move on to, so these are more like, giving us better understanding about these concepts. So it prepares us for our understanding of the boosting property. Okay. Also, when error is 0, the edge is gonna be 1/2. When error is half, the edge is gonna be 0. And the larger the edge is, the better quality the classifier has. Okay. So this weak learning condition, essentially, you can also think about it as there exists a gamma greater than 0. So the edge greater than 0 just means better than random guess for any data distribution over S and for any base classifier. Okay, so this is the so-called weak learning condition. Actually, it sounds very weak, but it's basically talking about the separability of the data, which is quite strong here, actually. Okay, so usually you wanted to use gamma to denote the lower bound of these gamma t's for any base classifiers. And this weak learning condition is assuming that gamma, the lower bound, is strictly greater than 0, cannot be equal to 0. But that's very important to note. Okay. So very, very importantly, this is the motivation why, atom boost is so interesting or it is so powerful. it has a very, very nice empirical error bound. So this theorem, we call it training error exponential decay. What it really means is that if you look at the empirical error of the classifier output by the outer boost algorithm that we just described, then the empirical error is gonna be upper bounded by exponential of this term here, exponential of -2 gamma squared capital T. So what does this mean? First of all, gamma by weak learning condition is greater than 0, strictly greater than 0. So this exponential term will have it will be exponential of a negative number. And more importantly, as T increases, then the empirical error decreases exponentially with respect to T. Okay? So this is a very good, seems to be very good result for the empirical error bound. Okay, it will quickly converge to 0 if your T increases. Any questions so far?
So just to confirm, that's
Right.
empirical error and not generalization, generalizability.
Yes, this is R hat, yes. We haven't talked about generalization ability yet, but we will.
Okay, thanks.
Okay, so anyone has any question regarding the result? So this is the first, very important result in outer boost. And actually through the proof, we will understand why we select epsilon that way, why we do the adaptive empirical distribution that way, why we combine the weak classifiers using alpha, and why we choose alpha that way. Okay, so through the proof we'll see, and that's why we will need to go through the proof this time for this theorem. But before that, let's see if there's any question from the audience. Okay, so a very important thing is to know that this is not a high probability bound. Okay, so we've seen generalization error bounds. Those are all high probability bounds, but this is not a high probability bound. It is just true, right? The empirical error will decrease exponentially as long as gamma is greater than 0, as long as you have the weak learning condition satisfies. Also, the training error decays exponential with respect to number of weak base classifiers. So if you just increase the number of base classifiers, then you will get a very good empirical error, guaranteed. So as I already hinted before, how you might want to understand how hard to achieve such gamma. And indeed, we will talk about that later on when we think about the generalization properties of this. But more importantly, for the empirical error understanding, wanted to focusing on the choice of alpha t and the choice of the adaptive distribution dt. Okay, so here, I wanted to use adaptive distribution just for simplicity. It's actually adaptive empirical distribution probability vector. But let me just use adaptive distribution so it is easier, for explanation. But whenever I say adaptive, I really don't mean that there is an underlying distribution where the data are sampled from, and this distribution is the adaptive. That's not what I mean. Okay, so from now on, when I say boosting, when I say adaptive, I really just mean that I put a weight, an adaptive weight, when I have for different base classifiers for these empirical examples. So to prove this theorem, again, I provided a proof sketch. The proof sketch essentially are divided into 3 steps. The first step, you wanted to prove that the R hat H, so the empirical error, will be upper bounded by the product of the ZT, product of the normalization terms. So this is the first step. Then once you do that, then you're going to individually upper bound each of the ZT. Okay, so each of the ZT is going to be upper bounded by 2 multiplied with square root epsilon t 1 minus epsilon t. Okay, so now you might want to, go back. Now you might get an idea of why, I don't know what's going on. Yeah, why I kind of select my ZT to be 2 times square root of epsilon t 1 minus epsilon t, okay? So that's basically because of how we were able to bound the ZT. So now, once I get an upper bound of each individual normalization term, then I say overall, I can upper bound the product by exponential of this term here, which is essentially what we have here, okay? All right, so is the proof sketch clear? It is a very simple proof sketch. Okay, if there's no questions, I'll move forward. So I kind of put the proof sketch on at the corner of the page. So just for your reference, in case you couldn't remember the proof sketch. So we are now at step 1. We're trying to upper bound the empirical error through the multiplication of these normalization terms. Now, first, let's consider this definition of the FTXI, okay? What is FTXI? FTXI essentially is, now I'm assuming that, for the first T base classifiers, I can do a, linear combination, okay? So that's why I use S to denote, the index of these base classifiers from 1 to T. So just not to confuse this with HS, we usually denote this as like the hypothesis that we learned based on a sample. So this is a little bit confusing notation here, but I wanted to emphasize this is nothing but an index for this. It's an index for the base classifier. Okay, I hope this doesn't confuse you. All right, so the alpha S is nothing but just the weight, the coefficient, how you do the linear combination of these base classifier. So, one thing is that based on the definition of the empirical distribution, dt plus 1 should be nothing but the exponential of this thing divided by this, right? So we've already proved this, remember? So let me go back to this here. You see that? Okay, so dt plus 1. You just do the recursion and you will get this expression here, okay? Questions? All right, so you get the dt plus 1i, which is this form here. Now, you can calculate the empirical error. So remember, what is the definition of empirical error? The definition of the empirical error for R hat H is nothing but the empirical distribution, so usually uniform, right? When we calculate the empirical error, we actually think all the examples uniformly. So it's gonna be 1 over m. Notice that this R hat of D is not dependent on any of this dt thing here, right? Okay, so this is nothing but just empirical error as we defined before when we first introduced pack learning. So this, I hope this doesn't confuse you. Now, so it's defined as 1 over m, summation of these in 0, 1 loss function, okay? So now this one, because of this figure here on the right-hand side, you can see this 0, 1 loss function is actually upper bounded by the exponential function. Why do I do that? Simply because this step function, this 0, 1 step function is not differentiable. So I get a relaxation of this loss function using this red curve here. Notice that this y-axis is yi multiplied with ftxi. So if you notice, if you use this as your x, right, you can see then the 0, 1 loss is nothing but this step function, the blue thing here. Why? Because when yi ftxi is smaller than 1, then the loss is going to be 1. It's smaller than 0, then the loss is going to be 1. It's greater than 0, then the loss is going to be 0, right? Just the 0, 1 loss. Now, if you look at the exponential function, you know, and then it's going to be this red curve here. And it's very obvious that this exponential loss is going to upper bound the 0, 1 loss that's not differentiable. Actually, this kind of relaxation of the non-differentiable functions have, you know, we've done a lot, right, in machine learning research, or even, I don't know, other computer science research. Okay, so you get this upper bound. That's why you have a smaller than equal to here. Now, once you get this exponential function, actually, you know, because, do you guys see? Because we are doing the exponential relaxation here, and that's why we are kind of using the exponential way to adaptively change the empirical distribution dt. Do you see? So, you know, you will see, after you see the proof, you will see why we kind of use this way to adaptively change the empirical distribution of these points. Oh, sorry. Okay. So once you get this, you will see this exponential of minus yif txi is nothing but this term here. I'm just reverse, you know, because of that, you can just reversely put this here, right? Because of this equation here. Do you see? Right, so this exponential term just becomes a multiplication of this dt plus 1 multiplied with this m. Only difference that now I've replaced the small t with capital T here, but it is the same. Okay. All right, so once you have that, then, you know, what can you do? You can just take the m out. Why? Because m is independent of the i's. So you can just take m out, and this term cancels, right? And then what happened? You can also take the product out. Why? Out of the summation, why is that? Yeah, doesn't depend on I, right? So you can just take that out, then essentially it becomes this form here. Okay? Now what's going on? So you have this term, and you multiply with this term. You know that the dt plus 1 has to be a distribution vector. So the summation of dt plus 1 over all its elements is going to be 1. Therefore, this RT, R hat H is going to be upper bounded by the product of the ZT. Okay, a very simple proof here. The only relaxation is this relaxation of the 0, 1 loss to the exponential loss. Okay, so far so good. Okay, someone's saying go faster. Okay, step 2. Step 2 is bounding the ZT. So ZT is a normalization factor, right? It is essentially defined as the summation of the dt exponential minus alpha tyi htxi. Okay, why do you have that? because it's a normalization term, right? So if you wanted to make sure it is a probability vector, you want to make sure the summation of the dt plus 1i equals to 1. And you know that this dt plus 1i equals to dti exponential this term divided by zt, right? So therefore, you should wanted to make sure that the zt is the summation of this. Okay? So we know that the zt is that. Then, as we also said before, summation of all the examples can be divided into two subsets. One is the, correctly classified, the other is the wrongly classified, right? So once you do that, you know that the correctly classified would have this being 1, the wrongly classified would have this being -1. Therefore, this is going to be dt exponential minus alpha t, and exponential here is the alpha t. Okay, so also based on our definition, we know that this summation of the dti on the wrongly classified ones will be epsilon t. So for this term, it's going to be 1 minus epsilon t, because this is the probability of the correctly classified. So it's 1 minus epsilon t. And this term is going to be epsilon t. Okay? And you can see here, we're making things much simpler because we allow our labels to be only -1 and +1. We're also, the ground truth is also -1. Ground truth label is also -1 +1. So it makes things much simpler. Okay. So the zt essentially just becomes 1 minus epsilon t exponential minus alpha t plus epsilon t exponential power alpha t here. Okay. So now the question is, if you know the zt, because I said you wanted to upper bound the zt, right? So as also you know that the empirical error is upper bounded by the product of the zt. So it makes sense to make the upper bound of the zt as tight as possible. So how do you choose that, right? You know that zt has this star form here. How do you choose alpha t to minimize the zt? So essentially, because it's convex and differentiable, you can just set the derivative to be 0 to get the alpha star here, right? So we're all familiar with this. So essentially what we do is we can just set the exponential to be 0, so set the derivative to be 0, then you can calculate the alpha t to be a half of logarithm 1 minus epsilon t divided by epsilon t. Okay, so this alpha t is selected by doing that. I didn't put all the steps here, but essentially if you take the derivative, you'll see how to get that alpha t. Now, once you get the alpha t, you can just substitute it back, and you can see that the zt essentially is upper bounded by this term here. Okay. Okay, if there's no questions, I'm worried people might get bored. Someone's calling me, please go faster. So, if you think it's too slow, I can go faster.
That was just trying to say that I had no questions, but I do actually have a silly question here.
Okay.
I don't see any relaxations happening anywhere for step 2. So relaxations, like
relaxation.
We had,
oh yeah. So the relaxation really depends on the alpha choice, right? Yeah, there is no relaxation indeed, but we can achieve the equality, but it's through the choice of the alpha t. We've chosen an alpha t that minimizes this zt.
Yeah.
So what I'm saying here, essentially, why I have a smaller than equal to is because I think through other choices of alpha t, this. Oh, I see what you're saying. Okay, I think I misunderstand your question, right? So you're saying that we are getting a ZT that is exactly this form here, right?
Yeah.
And we don't know how ZT could be possibly smaller than that term, right? Is that what
Yeah.
you're asking? Or did someone wanted to make a comment? Yeah, actually, I think it's fair to say that ZT is equal to this. We can make ZT to be equal to this one, right? By through selection of alpha t. So maybe this way, saying upper bound is a little bit strange here. Okay. Oh, did I miss people? I couldn't hear anything now. Hello?
I don't
Do you
think
hear
anybody
me?
said anything.
Oh, okay.
Oh, so is alpha fixed? Because this would be an upper bound if alpha is not fixed.
Well, if alpha is, chosen other way, then actually your ZT could be greater than this, right? Is that true? Because we're chosen alpha t to minimize the ZT here. Do you see?
Okay, so ZT is greater than this
Yeah.
final line.
But actually, I should say, we can find the ZT that is equal to this. Maybe that's more precise. We can
By setting the
there
alpha.
exists, or how about this? There exists a way of selecting alpha t such that the ZT is going to be equal to 2 multiplied with square root of epsilon t 1 minus epsilon t.
Right.
Would that be okay?
So this is, so after step 1, we have to set alpha to a certain value.
Right. So step 1 is saying for any alpha, the r hat h is going to be upper bounded by the product of ZT, right? We didn't say the selection of alpha. Now we're saying if you select alpha in a way, that is here, what I'm highlighting here, then the ZT could be as small as 2 of the square root of this term. 2 multiplied with square root of this term.
Okay.
Okay. Yeah, this is indeed a little bit confusing. All right, so now, if now we're done with step 2, okay? So now we're at step 3. I wanted to upper bound the product of the ZT such that it is upper bounded by exponential of this -2 summation of these half minus error squared. So how did I do that? I look at the product of the ZT. I've already chosen my alpha in a way such that my product of ZT can be just the product of my 2, times square root of epsilon t multiply 1 minus epsilon t, right? I've already done that. I've selected my alpha that way. So that's why selection of the alpha is very important. Now, if you do that, then you can see this term, you can just manipulate the math, the expression, you can get this term, right? This is strict equality. Okay? If you expand this out, you'll see why. Now, what happens is using this property that 1 minus x smaller than equal to exponential of minus x, you can just get this inequality here, because for each of these terms, you will get that. Okay?
What about that 2 factor that's in front of the square root?
oh, this is, 1 minus x. So you have 1 minus x. How should I?
Did you miss a 4?
Can you say that again?
Or yeah, there's also, yeah, that
Yeah,
4.
so here you have a 4 here, see?
Should that 4 also be on the next line down?
Let me see.
Like -4/2.
Oh, this will be 2, right? Are you saying this will be 2 instead of 1/2?
Yeah, I think so.
Yeah, that's true. That's a typo. That's 2 instead of 1/2. Right. Yes. Yeah, so because I will just, take, because it will be my square root of 1 minus 2 epsilon t, right? This term squared, right? Okay. Then you'll get that. Then finally, because it's the product of the exponential, so it becomes exponential of the summation. Okay. All right, so then you get the final proof. And also because, your gamma, you know how to define the gamma t is just half of this, right? Is that half, or I don't remember if it's half or 2 multiplied. Oh, it's 2, right? 2 times, wait, let's go to the definition of the gamma. Yeah, it's the half, sorry, it's the half. So gamma is just the half minus epsilon t. So let's go back here. I think I don't have the half here. So gamma is just the half minus epsilon t. So then you can just replace this with exponential right, which essentially becomes exponential of minus 2t gamma squared t, right? Because the gamma t's are all small, greater than gamma. Okay. This is actually an inequality here. All right, so that's the entire proof of this empirical error for adder boost. Any questions? So the empirical error of the classifier output by the adder boost will verify that the empirical error is always upper bounded by exponential of this minus 2 gamma squared t. Okay, of course, again, this is very important that you can see the selection of the alpha t has to satisfy some value in order for the zt to be small. All right, so here, there is a slide talking about alternative loss functions. And indeed, please take a look at these, like the relationships. Your textbook is having this relationships between like selecting these loss functions, for example, coordinate descending logistic regression. So, if you're interested, I suggest you take a look at those and understand how loss functions might play an important role in these kind of applications. So now we don't have much time today. I don't know if I'll go through entirely the overfitting problem, but now we've understand that boosting seems to have a very, very desirable empirical error property. But what about overfitting, right? So actually, theoretically, if you look at the exercise, you will see that you will see that if you have VC dimension of H being D, okay, then if you look at, the strong classifier, essentially, right? So this is the strong classifier doing the sign of this, linear combination of the HTs. Of course, there is a shift term, but it doesn't really matter. You can just set the shift term to be 0. But the point is, if you have a VC dimension of the H to be D, then actually the strong classifier can be really rich. Michael was having this question earlier, saying, basically, if you have a linear combination of these base classifiers, how complex the resulting strong classifier can be. So as we can see, it can be arbitrarily complex, right? Because what really doing is, you are doing like a linear combination of these sign functions. So these sign functions are already, being, you already done some kind of non-linearity over that. Also, if you think about the growth function, right? What is this saying? So the growth function is saying, or the rather so-called the VC dimension argument is saying that, how many ways you can classify these M examples, right? So growth function is just saying how many ways your hypothesis can classify these examples in your hypothesis. Whereas the VC dimension is just saying, if you are able to find a shattering of M examples and you were not able to find a shattering of, if you're able to find a shattering of D examples, but you're not able to find a shattering of D plus 1 examples, then your VC dimension is gonna be D, right? So what this is saying is, if you do this linear combination of the base classifiers, you can see, based on the example we were saying, you can see that it's very likely that you will have very rich way of classifying all these examples, because the base classifiers can have very different result for each of these data points. Therefore, doing a combination of them, you can get very different results by doing the combination. Actually, there is an exercise that showing you that the VC dimension of this strong classifier is upper bounded by 2 times D plus 1 times T plus 1 logarithm of T plus 1e. So essentially, it's gonna be dependent with respect to the original VC dimension D, as well as the number of classifiers you have in your outer boost. So if your T is really large, then what this suggests is that your VC dimension is going to be very large and you might overfit, right? Because your T is simply too large. You wanted T to be large only because you can get a smaller empirical error, because remember, the empirical error decays exponentially with respect to the T here. Okay, so you see this discrepancy between, this suggests that the outer boost could overfit for a large T. Now, actually, what really happens is that empirical observation tells that when you do outer boost, so the x-axis are the number of rounds, when you do that, you will see the gap between the training error and the test error actually remains pretty not much changed from the smaller number of rounds to larger number of rounds, as large as 1,000 here. Okay, so what this really suggests is empirical observation tells us is actually not overfitting. Even if you increase your T to be 1,000, the gap between the empirical error, the gap between the training and the test error is still relatively small. Remember, in our learned generalization theory, the the gap between the test and the training is called a generalization gap. And the generalization gap often depends on the complexity of the hypothesis, right? Here, of course, they were fixing M here, right? For this example, for this plot, they're using the same number of training examples in the sample. So the M is fixed, but what is, the D actually differs, right? As our analysis here, when your number of rounds goes large, the T will be larger. So hypothetically, your empirical gap should be larger, but it turns out the gap is not changed much. So there basically is a discrepancy between the theory and the theory analysis and the empirical observations. So now the question is, how do we explain this, right? Is there anything wrong with our theory? Or, why couldn't our theory explain the empirical observation?
I have a question. On that picture, is that for linear classifiers?
Actually, I'm not sure, but I don't think it matters. So essentially what, this means is that, your hypothesis, for each of this hypothesis, it has a VC dimension D. But, this exercise tells us if you do the strong classifier, the VC dimension of the strong classifier will be, depending on the T, right? The number of classifiers.
For the linear classifiers with add a boost, is this equivalent to like a linear decision tree?
I guess you don't want it to say decision tree, right? Because the decision tree would be just like one classifier.
Well, the decision tree is one classifier, and then if you run add a boost, at the end you get one classifier.
Sure. You are like boosting the trees, I guess.
No, not using add a boost with a tree, just using add a boost with linear classifiers.
Okay.
So I was wondering if you could use the same theory for a decision tree for add a boost.
I don't know if I understand your question, but the point is, I gave you a simple example of a linear classifier as the base classifier, but we didn't make any assumption about the base classifier. It could be anything, as long as it satisfies the weak learning condition.
Okay.
I might have confused you because I just use a linear thing because it's easier to for visualization purpose. Okay. Okay, so people are, a little bit confused about the M. So, so let's clarify again. Because the generalization gap in our theory, the generalization gap not only depends on the VC dimension, but also depends on M, right? The number of examples in your S. Okay, so I'm simply saying that, you can see, although we say that VC dimension, when you have more rounds, should be larger, then, if your M is the same, then the generalization gap should be larger, right? But it is not what we observe here. We observe the gap remain pretty consistent, even if you increase the number of rounds. The number of rounds just means number of classifiers, or you can think about that as T. Okay. All right, so we see this, the gap between theory and empirical observation, but don't worry, we know what's going on. We'll see why. So the Rademacher complexity of convex halls, this is gonna be like a prerequisite for us to understand why we have this gap between theory analysis and empirical observation. First, let's recall our, recall the definition of the convex hull. What is a convex hull? If you have H, hypothesis class that is is the mapping from the input space to a real, then the convex hull of the H is nothing but this linear combination of UKHK. So what is this? So here, HK is one element from the hypothesis class H. Okay, so what this convex hull is saying, you're doing a linear combination of these HKs using mu k's. But one thing to notice that the mu k's have to be greater than 0, and the summations of the mu k's have to be smaller than 1. Okay, as long as you satisfy that, then the collection of these is going to be the convex hull of the H. Okay, right? So now with this convex hull, what's going on is that a nice lemma follows. It says that the empirical Rademacher complexity of the convex hull of H is equivalent to the empirical Rademacher complexity of the H. So what this means is that I have a hypothesis class. If you look at the complexity of the convex hull of this hypothesis class, I don't increase the complexity of my hypothesis after doing the convex. Okay. All right. So do people understand what this lemma is saying? And the proof is rather simple. The proof goes as, you have the empirical Rademacher complexity of the convex hull, and then essentially it becomes, by definition, becomes this term here, right? I'm doing nothing but plugging in the definition of the empirical Rademacher complexity and the definition of the convex hull, right? So here you can see I'm allowing this mu k's to be only greater than equal to 0, and I have to restrict the L1 norm of that to be smaller than 1, equal to 1, of course, smaller than equal to 1. Okay, so any questions here? Now, once I just expand this equation using its definition, then we can see here, it is nothing but doing, you can take the, the summation of this K outside here. And what happens is that then you put this thing inside here. So you basically haven't changed anything but a switch of the order for these two summations. Okay, the supraamount is still the same, and only difference is that you extracted this thing here. But since these two summations are exchangeable, so yeah, let me finish the slides and then we'll finish today's lecture. So this is fine, just exchange of summations. Then after that, you will see one thing that's very interesting is that, for minimizing this mu here. So what I'm trying to say is, if you wanted to maximizing the vector mu for the convex combination of p terms, it's going to be the one that's placing the weight on the largest term on the sum. Okay. So sorry, if you wanted to maximize the vector mu for the convex combination of p terms, then the solution is going to be the one that's placing weight on the largest term of the sum. Okay, so if you do that, then you will see it becomes this term. So you just maximize the k, and essentially the supraamount becomes just the any hk. Okay, so it becomes the summation of sigma I hkxi. Okay, and now you will see this is nothing but the definition of the empirical Rademacher complexity of H. Right, so this basically completes the proof, and using this key observation in the next lecture, we'll see why Although it seems like there is a gap between theory analysis and empirical observation. Indeed, later on, using margin theory, we're able to show that boosting doesn't overfit. Okay, and the convex hull is the key here. All right, thank you, everyone. Good luck with people who are doing ICLR submissions.
Thank you, Professor.
Thank you.
Thank you.